Hello, this is Jack Jackson. In this video, we're going to introduce our postulates for unified geometry, not all of them, just the first part, the incidence postulates. Um, so this is part one of this set of postulates. Now, in the last few videos, we talked about Euclid's original postulates, which were synthetic, Hilbert's excellent rephrasing of those and refining those um, based on the work of Euclid, but also many mathematicians between Euclid and Hilbert. But he came up with a set of postulates there that were very good for a synthetic approach. And then we also talked a little bit about Birkhoff's postulates, which are an analytic approach. And our postulates are going to be a hybrid of postulates similar to variations on Hilbert's postulates and a couple of Birkhoff's as well. Ultimately, we're going to put that together. So the incidence postulates we'll see here are very much like Hilbert's incidence postulates. These are also set up to be defined in such a way that we're going to use these for unified geometry for this class, and the references in parentheses refer to the corresponding postulates from other sets. So if you see E, it'll be the corresponding thing for Euclid, like if it says E2, that's Euclid's second postulate. H is Hilbert's, B for Birkhoff, K for K. K is our textbook. So the first thing you need to realize when you're doing a set of postulates, you need to go ahead and work with whatever postulates you're studying in that class. Now, I'm the instructor for this class, so we're going to use my postulates, my ball, my rules, right? So we're going to be setting these up, and I've set these up in such a way that these will be the ones that we're using. So we use my numbering, we'll use this. So you won't refer back necessarily to Euclid's, Hilbert's, Birkhoff's, or K's postulates, but you'll see that they are closely related to them. Okay. The first thing that we'll notice here in just a minute is that postulate 1 explicitly states that the geometry is all about sets of points. And by stating this postulate explicitly, we know that we can use the notation and basic results of set theory. So in all our studies of geometries, you may assume that this postulate is true even if it's not explicitly stated. So if we want to use any of the language of sets, talk about intersections and elements of and that sort of thing, that will make sense for us. We will also typically think of space as being a three-dimensional set, which we haven't really defined yet, but we will mostly be limiting ourselves to a single two-dimensional plane for most of our work. Even though space might have 2 dimensions, 3 dimensions, or even more than 3 dimensions. That's the concept of dimension is covered in the novel Flatland that we will be discussing some. I'll have you read. So we have some undefined terms, and they're the typical ones that almost everybody has to use. So intuitively, we may think of a point in Euclidean geometry as a location or a place that has no size. It's a location only. And then points then are the basic atoms of a geometry. Everything in the geometry is some set of points. However, this is not a definition. So we take the point, line, and plane actually as undefined terms, and those relationships among them are established by the postulates. So here we go, and I do use a color coding here. If it's a postulate, it's going to be in red, definitions are purple, and then comments are in green, and propositions are in blue. So that can maybe help you just a little bit keep track of what kind of statement it is that we have. So here we go. Our very first postulate is the collection of all points in a geometry forms a set called space. So space is it's a universal set for all the points in our geometry. And we're going to have a definition. Any non-empty set of points in space is known as a geometric figure. So it could be a set containing 1 point, 2 points, infinitely many points, points in different shapes. That's a geometric figure. Postulate 2 says lines and planes are geometric figures. So right away we know that lines and planes are sets of points. Non-empty sets of points, actually. Okay. We have a few other definitions and notations here. We say that two geometric figures are equal if and only if they represent the same set of points. In other words, the set of points are equal as sets. So they not only have to be the same size and shape, but the same location as well. They have to be the exact same set of points. We'll get to the idea of congruent a little bit later, but for example, if you have a line segments that are equal length, they are not equal line segments unless they are just two different names for the exact same line segment. So an equal length line segment at a different location we would call a congruent line segment. We'll define what we mean by that a little bit later on down the line, probably next week. So definition number 2 is if a point A is an element of a line and a plane, then we say the point is on the line and in the plane, and that the line and the plane contain the point. We also say the line goes through the point, and similarly we say a line lies in a plane if it's a subset of the plane. So contain, on, goes through, lies in, those are just element or subset relationships, right? So that makes sense since we're talking about sets of points. Number 3, we say that a set of points is collinear. Notice the spelling, it does have 2 L's there. Collinear if and only if there exists at least one single line containing all the points in the set. Non-collinear is the negation of collinear. So if a set of points, whether that's 2 or 3 or 4 or 5 points or infinitely many, if it's collinear, that means there is a single line that contains every single point in that set. If it's a non-collinear set, it says that there is no line that contains all of the points in that set. It may contain some of them or none of them, but it doesn't contain every single one. Okay. So another way to think about that is if you have a non-collinear set of points and you have a line, there's at least one point in that set that's not on the line. 4, we say that a set of points is coplanar if and only if there exists a single plane containing all the points in a set, and non-coplanar is a negation of coplanar. So my similar comments about planar and coplanar would apply to the ones I made for collinear and non-collinear. So note that the definitions and postulates above allow us to use basic set theory in our description of points, and the next several postulates guarantee the existence of at least some points, lines, and planes in the geometry, and they give some basic relationships among these undefined terms. So postulate 3 says there exist at least 4 non-collinear, non-coplanar points. That's like Hilbert's incidence axiom 7 and K's incidence axiom 5. Postulate 4, every plane contains at least 3 non-collinear points. So let's back up to postulate 3 first. There exist at least 4 non-collinear, non-coplanar points. So there have to be at least 4 points in the geometry. That's guaranteed right there. And it also says that of those particular 4 points, not any 4 points, but those particular 4 points that are guaranteed there, there's not a single line that contains them all and not a single plane that contains them all. Postulate 4 says every plane contains at least 3 non-collinear points. So if we have the plane, then there are going to be some points, at least 3 points on that plane, and that are not all on the same line. Postulate 5 says every line contains at least 2 points. So here notice we're starting with the line, and then we have to get 2 points that are on that line as a consequence. This is Hilbert's axiom I7 and K's axiom I5. Postulate 6 says given any 2 distinct points, there exists exactly one line that contains both of them. This is Hilbert's axioms I1 and I2. I think it's I1 and I2. One of them had exactly one. It had at least one, and excuse me. His axioms had one of them had at least one, and one had at most one. Put those together in one statement here. Exactly one line containing both of them. So notice the difference in postulate 5 and 6. In postulate 5, you're starting with a line and saying that there have to be 2 points on it, whereas postulate 6, you're starting with 2 points and saying that it must have a line containing it. This is Birkhoff's postulate 2 and Kay's postulate 1. So a lot of these are the same postulates that we've seen in other sets, perhaps it's phrased slightly differently, perhaps in a different order, but they're basically equivalent. We say that 2 points determine the line if and only if postulate 6 is true. So determine a line, 2 points determining the line means given any 2 distinct points, there exists exactly one line containing both of them. So if there's a unique line containing points in A and B, we can call it AB with this little double arrow line thing over the top. That's the symbol we use for line AB. Okay, and we haven't gotten there yet, but we will eventually use this notation AB with the lines over it without the arrows to be a line segment. AB with the arrow on one end for array, AB containing A and B with the endpoint A. And then we'll just use AB for a number, the distance from A to B. We'll get to those concepts a little bit later, but I just want to point out right off the bat that the notation is going to be important, that we're careful about that. Okay, notice we cannot use this notation for a line unless we first know that postulate 6 is true, or at least that for those particular 2 points, A and B, there is exactly one line containing them. Has to be a line containing them, and at least one, and at most one line, exactly one line. Okay. I think I already said all this stuff. So again, line, this is line AB. Later on, this is going to be line segment AB, ray AB. Those are 3 different geometric figures. And then we have AB, which is just a number, which is not a geometric figure at all, but rather a real number. And that's going to be the distance from A to B. So be careful that you're consistent about this. One of the things, this is a really easy thing to get right if you just pay attention. So it's a matter of paying attention to detail. All right, next, postulate 7. Given any 3 distinct non-collinear points, there exists exactly one plane containing them. That's Hilbert's incidence axiom 4 and 5. Definition, we say that the 3 non-collinear points determine a plane if and only if postulate 7 is true. And we represent the unique plane containing the non-collinear points A, B, and C as plane ABC. Postulate 8, if 2 points lie in a plane, then any line containing them lies in the plane. That's the same as Hilbert's axiom I5 and Kay's axiom I3. And postulate 9, if 2 distinct planes intersect, then their intersection is a line. That's more or less Hilbert's I6 and Kay's I4. So there are 9 postulates about existence and incidence. And from them, we can prove these 5 propositions right off the bat. Proposition 1 says there exist at least 6 distinct lines and 4 distinct planes. Now, in Euclidean geometry, we're actually having infinitely many distinct lines and infinitely many distinct planes, but so far, these postulates here only are going to guarantee this much, but they do guarantee this. Of course, we already had up above there 4 points. Proposition 2, well, let me just say this. One of the homework problems will be to actually make a model of a geometry that obeys all 9 postulates. It only has 4 points, 6 lines, and 4 planes. So a finite geometry that does that. And of course, Euclidean geometry satisfies all these postulates as well. Proposition 2 says if 2 distinct lines intersect, then they intersect in exactly 1 point. That's actually a consequence, I think, of just one of the postulates. Proposition 3, if a line intersects a plane not containing the line, then their intersection is exactly 1 point. Proposition 4, given a line and a point not on the line, there exists exactly 1 plane containing the given point and the line. We have a couple more definitions. 2 lines are parallel lines if and only if they are coplanar and non-intersecting. Two lines are skew lines if and only if the union of the two lines is non-coplanar set of points. Proposition 5 says if two lines intersect, then the union lies in exactly one plane, and part B of that, skew lines do not intersect. This is really two different propositions, but they're closely related, so I made them 5A and 5B in terms of the numbering. I'll do that a lot of times. I'll group together a set of propositions that are related to each other. So here we have 5 propositions that can be proved from the postulates above. This is our set of what we would call incidence and existence postulates. This is not a full list of all the postulates, but from these, we're going to work through these the first week or maybe even part of the second week, talking about what can we prove just from this. Okay, we'll see if we can prove some of these things here, and we can look at some different finite geometries that obey these, and then maybe what happens if we change some of these postulates, what would happen to the geometry. We'll look at some of those ideas as we go forward.